In this paper, we adopt a relational view of analogies applied to semantic role classification in FrameNet. We define analogies as formal relations over the Cartesian product of frame-evoking lexical units and frame-element pairs, specifically, as binary relations between predicate-argument pairs drawn from the same semantic frame. Each instance in this relation is labeled as valid if the two frame elements share the same semantic role, and invalid otherwise. This formulation transforms semantic role classification into a binary classification problem, enabling us to train a lightweight artificial neural network with minimal parameters and rapid convergence. Crucially, during training, the model receives no explicit semantic role labels, only the structure of the analogy itself. Instead, semantic roles are recovered at inference time through analogical transfer, by sampling random annotated sentences from the same frame, constructing analogy quadruplets, and computing probability distributions over all possible semantic roles. The role with the highest aggregated score is assigned to the target frame element. This approach not only surpasses previous state-of-the-art results on FrameNet 1.7, but does so with exceptional computational efficiency and model frugality. The entire pipeline, embedding extraction, model training, and inference, runs on a single Tesla V100 GPU in under 15 minutes, consuming just watt-hours. It achieves an overall accuracy of 79.3% on the test set, outperforming prior methods even when integrated into end-to-end parsers like Lin et al. 2021 and Swayamdipta et al. 2017. To understand why this works, we must first ground our approach in cognitive theory. Analogical reasoning is not merely a computational trick. It is a core mechanism of human cognition, central to concept formation and learning. As Hofstadter and Sander argue in Surfaces and Essences, analogies arise not from static word similarities, but from the alignment of relational structures across contexts. This insight underpins our framework. Validity depends not on lexical proximity or vector arithmetic, but on whether two frame elements play the same semantic role within a shared frame. Consider this example. In the sentence, decomposed leaves provide a fertilizer for the trees. The frame is supply, with leaves as the supplier and trees as the recipient. Now consider, lentils furnish proteins to humans. Here, lentils are the supplier, humans are the recipient. Same frame, same role structure. Despite different lexical content, the semantic mapping is identical. This is where our method shines. Rather than relying on word embeddings alone, we encode the relational structure of the frame. For any target frame element, we sample source instances from the same frame, build analogical quadruplets like provide decomposed leaves, furnish lentils, and submit them to our trained binary classifier. If the model classifies the pair as valid, we transfer the source's semantic role to the target. This process is inspired by the structure mapping theory, Gentner, 1983, which posits that analogical validity emerges from the systematic alignment of relational roles, not attributes. In this light, our model isn't learning semantic roles. It's learning when two roles are structurally equivalent. Our dataset construction is systematic. From FrameNet 1.7, we extract all predicate-argument pairs per frame, then form the Cartesian product within each frame to generate all possible analogical instances. Positive instances are those where both elements share the same semantic role. Negative instances are all others. We balance the training set to mitigate class imbalance and train a simple feed-forward neural network with two intermediate blocks, Ray-LU activation, dropout rate of 0.3, and geometric feature reduction. With only ~800,000 parameters, it converges in under 7 minutes with near-perfect accuracy on the development set. At inference, we treat each frame element as an independent classification task. For a given target pair, PT, ET, we sample 7 representative source pairs per semantic role based on minimum occurrence thresholds, compute the model's predictions, and aggregate scores across all positive classifications. The role with the highest total score is assigned to the target. This decoding mechanism is both robust and interpretable. Unlike black box classifiers, the model's reasoning can be traced. This role was assigned because it aligns with 5 out of 7 similar instances in the same frame. This transparency is not incidental. It is central to our design. We evaluated our method in multiple settings. First, as a plug-in module in Lin et al.'s end-to-end parser, we achieved 49.81% accuracy, up from 48.95%. Second, integrated into Open Sesame with gold frame and span inputs, we improved from 58.46% to 59.35%. Most strikingly, when evaluated on gold frame types and frame elements, our method achieved 80.77% precision, 79.26% recall, and 79.17% F1, significantly outperforming 2 strong baselines that use BERT embeddings directly on the frame element or on the predicate element pair. Why does this work so well? Because we're not just classifying roles, we're transferring meaning through analogy. The model learns to recognize when 2 roles are functionally equivalent, regardless of surface form. It generalizes across unseen frame types and roles with minimal degradation, losing only ~4% accuracy on frame types absent from training, and ~7% on roles missing from development data. Moreover, our method is inherently scalable. When new semantic roles emerge, we don't retrain the model. We simply add new annotated examples to the reference pool. The analogical transfer mechanism adapts instantly. This is a critical advantage over traditional classifiers, which require full retraining or fine-tuning. We also tested sentence embeddings as context representations, without BERT. Performance dropped by 4%, but still remained competitive. This suggests that even coarse contextual signals can support analogical reasoning, opening doors for applications where fine-grained embeddings are unavailable. Looking ahead, we envision extending this framework beyond semantic role classification. Analogical transfer could enhance knowledge graph completion, cross-lingual transfer, or even explainable AI in medical or legal domains. The core idea, that meaning is transferred through relational alignment, not feature matching, offers a powerful alternative to current embedding-based paradigms. In conclusion, we present a novel, efficient, and interpretable approach to semantic role classification grounded in cognitive science. By reframing analogies as structural mappings between frame elements, we transform a complex multi-class problem into a simple, explainable binary classification task. The result is not just better performance, but a model that reasons more like a human, learns more efficiently, and scales gracefully. This work points toward a future where AI doesn't just classify, but understands, through analogy.